Alright, let's have a look at the homework solutions to topic 9. Okay, let's start from question number 3. ABCDEF is a regular hexagon with side length 9. And the question asks you to find the side length AD and the area of ABCDEF and then the length of AC. Okay, first of all, we can draw a regular hexagon which looks like this. Okay, let's call this point A, B, C, D, F respectively. And we can draw the diagonal AD, BE, and CF. And because it's a regular hexagon, we know that they must intersect at one point here, right? Let's call this point O. And we have learned in our lesson that these diagonals divide the regular hexagon into 6 congruent equilateral triangles, right? Therefore, we can easily find the length of AD, which is AO plus OD, and that gives us 9 plus 9, which is 18, right? And next, if you know the side length is 9, and of course we can find the area of each of the equilateral triangles, right? So the area of the hexagon is the total of the area of all 6 equilateral triangles, or could say the area of ABCDEF just equals 6 times 9 square root 3 over 4. So note that if you know the side length of a equilateral triangle, it's very easy to find this area, right? There's a formula we can use to find this area. And therefore the area of ABCDEF is 243 square root 3 over 2. And also note that if the question does not ask you to write round up or round down, always keep the exact solutions, okay? Okay, question C, find the length of AC. So we know that by symmetry, AD bisects angle CDE, right? Therefore, we know CDA, angle CDA here is 1/2 of angle CDE, which is 6 degrees. And if we connect AC here, we know that CD over AD is 9 over 18, which is 1 over 2. And angle CDA equals 60 degrees. And therefore, triangle ACD is actually a right triangle, right? Just 30, 60, 90 triangle. And therefore, we know AC should equal square root 3 times length of CD, which is 9 square root 3, right? Okay, have a look at the solution here. Let me know if you have any questions, okay? Alright, if no questions, let's have a look at the next one. Question number 6. measure of each exterior angle of a regular polygon is 1/8 of the measure of an interior angle, how many sides does the polygon have? So in this case, we could let the measure of each exterior angle be x. So we know the exterior angle is 8x, right? And we know that x plus 8x, the sum of the exterior angle and corresponding exterior angle, equals 180 degrees. And therefore we know x is 20 degrees. Therefore each exterior angle is 20 degrees. So the number of the sides can be calculated using 360 degrees over 20 degrees, right? Which is 18. Any questions? Alright, then let's have a look at the next one. Question number 7. Again, we have a regular hexagon, EFGHIJ. We are to find the ratio between EH and EG. Okay, first of all, let's draw the diagram to illustrate the regular hexagon. Okay, suppose this point is E, this point is F, E, F, G, H, and then I, J. And we know that by symmetry, long diagonal EH, which is this side, bisects angle FEJ. And therefore we know angle FEH is 1/2 of angle FEJ, which is 60 degrees. We know each of the interior angles of a regular hexagon is 120 degrees. And since EF equals FG and angle EFG is 120 degrees, then we have angle FEG equals angle FG equals angle FEG, which is 180 minus 120 over 2, and that's 30 degrees. And therefore angle GEH equals angle FEH subtracted by angle FEG, which is 30 degrees. This angle is also 30 degrees. And also we have angle HGE equals angle HGF minus angle FGE, and that gives us 90 degrees, right? And therefore we know triangle EGH is a right triangle, which is actually 30, 60, 90 triangle, right? With hypotenuse EH and short leg GH. And in that triangle, we can easily find the ratio between EH and EG, right? Which is 2 over square root 3, and then we need to rationalize the denominator, so that's 2 square root 3 over 3. Okay, have a look at the solution here. Let me know if you have any questions, okay? Alright, if no questions, let's have a look at the next one. Number 8. I can see a lot of you haven't done this correctly, so as I draw the regular octagon, please have a look at this question by yourself again, okay? ABCDEFGH is a regular octagon, so it will look like this. Okay, let's call this point A and B, C, D, E, F, G, H. Okay, so let A, B, C, D, F, G, H be our octagon here. We can draw AC because we are trying to find AC, AD, and AE, right? So let's draw these segments. Connect AC, AD, and AE. Okay, in this case, we know that ABCD is a trapezoid, right? So usually if we have a trapezoid like this, we can also draw the altitudes from B and C. To help us solve this problem, let's call this point Q and P here, and therefore we have angle QCB is 180 degrees minus angle CQA. Which is also 90 degrees, right? So angle DCQ is angle DCB minus angle QCB, which is 45 degrees. Okay, then we know that triangle CDQ here, this little triangle here, must be a right triangle, right? And it's a 45, 45, 90 right triangle. And similarly, angle ABP is also such a triangle, right? And therefore we know in these little triangles we have DQ equals PA, which is AB over square root 2, right? And we know that AB is 8, so 8 over square root 2 is 4 square root 2. And we also know that BCQP is a right rectangle. And QP equals CB or BC, which is 8. And therefore we have AD equals AP plus PQ plus QD, right? And we know that AP and QD are 4 square root 2 each, so plus PQ, which gives us 8 plus 8 square root 2, right? That solves the length of AD. Okay, next let's have a look at the length of AC. Okay, from the right triangle ACQ, we have the following relationship. AC equals square root of AQ squared plus CQ squared, right? And we know that AQ is A plus 4 root 2. So that is square root of AQ is 8 plus 4 square root 2, and then squared plus CQ squared. CQ is just 4 square root 2, right? So put this number in, you have AC is just 8, then square root of 2 plus square root 2 after simplification. Again, if the question does not ask you to round up or round down, always keep it as exact solution here. And then let's find AE. So since angle CDQ is 45 degrees, we have angle ADE is the angle CDE minus angle CDQ, and that gives us 90 degrees. And from, we can make use of the other right triangle. From the right triangle ADE, we can have the second theorem. AE is just a square root of AD squared plus DE squared, right? And we know AD and we know DE, so just put these two numbers in. That's 8 plus 8 square root 2 squared plus 8 squared, and eventually we have 8 square root of 4 plus 2 square root 2. That's the length of AE. Alright, so have a look at the solution here. Any questions, just let me know, okay? questions, let's have a look at the next one. Question number 9. Regular pentagon and the regular hexagon share a common side AD, as shown on the right. What is the degree measure of angle BAC? So we know that each interior angle of a regular hexagon is 120 degrees, right? And we also know that each interior angle of a regular pentagon is 108 degrees. And therefore we can easily solve angle CAB or BAC can be calculated by using angle VAD minus angle CAD. And in that case, that's the interior angle of the regular hexagon subtracted by the interior angle of a regular pentagon, which is 108 degrees. And the difference is just 12 degrees, right? Okay, any questions? Alright, then no questions. Let's have a look at the next one. Number 10. The pentagon ABCDE at right has a right angle at A and given that AB equals AE and ED equals DC equals CB, which is 1. And it says if BE equals 2 and BE is parallel with CD, what is the area of the pentagon? So first of all, let's connect VE. And since AB equals AE, and we also know angle A is 90 degrees, right? So angle AB is a 45, 45, 90 triangle. And we are also given that BE is 2, right? So if you know one side in that triangle ABE, you know the other two sides. So AB equals AE equals square root 2, right? If you to verify this, AB squared is 2, AE squared is 2, 2 plus 2 equals BE squared, right? So that verifies our calculations here. And also you can calculate the area of angle ABE, triangle ABE, which is 1/2 of AB times AE, and that gives us 1, right? And if you want to find the area of the pentagon, we also need to find the area of BCDE. So we could draw the altitude from C to BE, and let the foot of perpendicular be F. So we need the length of CF. We need altitude, right? So if you know this side, and altitude CF, then we can find the area of BCDE. So we can make use of the right triangle BCF. Right triangle BCF. We have BC equals, well, BE minus CD, right? Then over 2. Which is 1 over 2. Oh, sorry, my bad. That should be a BF, not BC. Because once you draw this altitude, well, let's call the foot of perpendicular BG, then CDG is actually a rectangle. Therefore, BF is 1/2 of B minus CD, right? And we also know that length of BC is 1, and CF is square root 3 over 2. And then from the right triangle, okay, so in the right triangle BCF, we know BC is 1 and BF is 1 over 2. Therefore, you can calculate CF, which is square root 3 over 2, right? Therefore, you know the height of the trapezoid. Then we know that the area of the trapezoid BC, sorry, DE is 1/2 of CD plus BE times CF, which is 1/2 times 1 plus 2 times square root 3 over 2. That's 3 square root 3 over 4. And therefore we know the area of the pentagon, which is ABC, BCDE equals the area of triangle ABE plus the area of the trapezoid BCDE. And that gives us 1 plus 3 square root 3 over 4. Okay, have a look at the solution here. Any questions, just let me know, okay? Okay, let's have a look at the next question, number 11. Find the sum of the angles at the points of a 7-pointed star A, B, C, D, E, F, G. And the heptagon in the center is not necessarily regular. So basically we're trying to find the sum of angle A, B, C, D, E, F, and G. So we could make use some interior angles of the heptagon. Okay, for example, we could let the measures of the 7 interior angles of the heptagon be x1, x2, x3, x4, x5, x6, and x7 here. Okay, first of all, let your readers know the meaning of x1 to x7. So we could say let the measures of the 7 interior angles of the heptagon be x1, x2, and all the way to x7 as shown in the diagram. The sum of these angles is we know the sum of the interior angles of a n-gon is 180 degrees times n minus 2, right? Therefore, we have 7 minus 2, which is 900 degrees, right? Okay, then we could have, for example, if okay, next let's use a quadrilateral A, C, E. Well, let's call this x6, for example. This point is x7, this point is x1, x2, x3, x4, x5. Okay, for example, if we could make use of the quadrilateral ACE x6, then in quadrilateral ACE x6, we know the sum of these angles: angle A plus angle C plus angle E plus angle x6, right? Should equal 180 degrees times 4 minus 2, which is 360 degrees, right? And similarly, you could also consider some other quadrilaterals. For example, B, D, F, X7, right? So how many quadrilaterals we can use there? We have 1, 2, 3, 4, 5, 6, 7. Sorry. We could use 7 quadrilaterals, right? So similarly, we have angle B plus angle D plus angle F plus x1, x7 equals 360 degrees as well, and also angle C plus angle E plus angle G plus x1 also equals 360 degrees. So following this pattern, we also have angle D plus angle F plus angle A plus x2 equals 360 degrees, and angle E plus angle G plus angle B plus x3 is also 360 degrees, and angle F plus angle A plus angle C plus x4 equals 360 degrees, and angle G plus angle B plus angle D plus x5 equals 360 degrees. Okay, so basically we have x1 to x7, 7 unknown quantities and 7 equations, which means we can solve these 7 unknown quantities, right? So for example, if we call them number 1, 2, 3, 4, 5, 6, 7, equation number 1 to number 7, we could sum them up, right? And the left side becomes well, we have A here. Basically, we have 3 A's, 3 B's, 3 C's, 3 D's, and 3 E's, 3 F's, 3 G's. So the left side becomes 3 of angle A plus angle. I'll just write here. Write it to the next row. All right, this gives us 3 times angle A plus angle B plus angle C plus angle D plus angle E plus angle F plus angle G, right? Then the sum of x1 to x7, right? Okay, I'll use this notation here. I from 1 to 7 of xi's. And the right side is just 360 degrees times 7, because we have 7 equations, which becomes 2520 degrees, right? And simplify this will give us the desired sum, angle A plus angle B plus angle C plus angle D plus angle E plus angle F plus angle G just equals 2520 degrees subtracted by the sum of x1 to x7, which is 90 degrees, divided by the 3, right? The coefficient in front of that. So that gives us 1620 over 3. That's 540 degrees, right? So final solution is just 540 degrees. Okay, did you get it? Any questions? Alright, if no questions, let's have a look at the next one. Okay, let's have a look at one more question, then we can take a 10 minutes break, okay? Next one we're looking for is question 14. Okay, so here let ABCD be a square and ABEFG a regular pentagon. In the diagram at right, we're trying to find angle BCE, the small angle here. Okay, first of all, because ABCD is a square, we have angle ABC is 90 degrees, right? And because ABCDE is a regular pentagon, we have angle ABE is 108 degrees, right? Therefore, we know angle CBE can be calculated by 360 degrees subtracted by angle ABC, then subtracted by angle ABE. Which gives us 162 degrees. And we also know that BC equals AB equals BE. Therefore, we know triangle BCE is isosceles, right? Is angle BCE equals angle BEC, and that can be calculated by 180 degrees minus angle CBE divided by 2, and that gives us 9 degrees, right? So the final solution is 9 degrees for angle BCE. Alright, have a look at the solution here. And if you don't have any questions, let's take a 10 minutes break. And after that, we'll have a look at question 15, okay? All right, next let's have a look at question number 15. Okay, we have a regular octagon, so let's draw this octagon first. Okay, and diagonal AE, so let's connect AE, CG, meet at X. And because it's a regular octagon, we know X must be the center of that octagon, right? And point M is the midpoint of AB. Alright, so this is what we have here. First, we need to find the angle XAB. Alright, so in the first question, we know each interior angle is (180° minus 360 degrees over 8, right? That gives us 135 degrees. And by symmetry, we know that XA bisects angle HAB. Therefore, we know angle XAB is 1/2 of angle HAB. And that gives us 67.5 degrees. That answers the first question. So for the second question, we know X is center of the octagon, meaning it's equidistant from all 8 vertices of the octagon, right? Therefore, we know by SSS congruence, we see that connecting X to each of the vertices forms 8 congruent isosceles triangles. Which means these triangles are all congruent by SSS. The vertex angles of these triangles are the angles at X. Since these angles are all equal, each is 360 over 8, which is 45 degrees, right? Since M is midpoint of AB, we have AM equals BM. And combined with AX equals BX and XM equals XM, we have triangle AMX must be congruent to triangle BMX. Also by SSS congruence, right? And therefore we know angle AXM equals angle BXM, which is just 1/2 of angle AXB, and that is 1/2 of 45 degrees. That equals 22 22.5 degrees. Okay, then let's have a look at question C. We need to find angle MXD. We know angle MXD equals angle MXB plus angle BXC plus angle CXD, right? And we know MXB is 22.5 degrees, BXC is 45 degrees, CXD is another 45 degrees. So that gives us 112.5 degrees in total for angle MXD, right? Okay, have a look at the solution here and let me know if I have any questions. Alright, then next let's have a look at question 16. Okay, again we have a regular hexagon A, B, C, D, E, F. Okay, first let's draw a diagram to illustrate the situation here. And we need to find the ratio of the area of ABCE. To the area of the hexagon. Okay, so in this figure here, altitude Vx. Okay, for example, we draw the altitude from point D to C and let the foot be x here. And then we know altitude dx of isosceles triangle DCE divides DCE into 2, 3, 60, a 30, 60, 90 degree triangles, right? So we could let the side length of the hexagon be S, for example. Then we have bx then equals S over 2, right? And also we have xe equals xc equals square 3 over 2s, right? This is what 30, 60, 90 degree triangles tells us. Therefore, we know EC is twice of that length, which is square root 3s. And therefore, the area of the triangle CDE can be calculated, which is 1/2 of EC times XD. And that gives us square 3 over 4s squared, right? And we could use similar method to find the area of triangle AFE. So you could just say similarly, the area of triangle AFE can also be calculated, which is exactly the same with triangle CDE, right? Which is also square root 3 over 4s squared. Okay, so we have done a exercise. If you know the set length, you should be able to calculate the area of the whole regular hexagon, right? Because it's just 6 congruent equilateral triangles. So we know that the area of A, B, C, D, E, F. I'll just write it directly, okay? If you don't know how to calculate that, just let me know, okay? So that area is 3s squared square root 3 over 2. So the area of A, B, C, E can be calculated by using the area of the regular hexagon subtracted by triangle CDE and subtracted by the area of triangle AFE. And that gives us S squared square root 3. And then we can calculate the ratio. Of the area of ABCE to the area of the regular hexagon ABCDEF. That is S squared square root 3 over 3s squared square root 3 over 2. And that gives us 2 over 3, right? So the final solution is 2 over 3. Okay, any questions? All right, if no questions, let's have a look at the next one. Question 17. Okay, all of the interior angles of octagon EFGHI are 135 degrees. EF equals GH equals IJ equals KL equals 2, and FG equals HI equals JK equals LE equals 6. Find the perimeter of the octagon, and find the area of the octagon, and find the length of EI. Okay, first of all, let's draw a diagram to illustrate the situation here. So we have a octagon. So we need 8 sides. So it probably look like this. And then we connect these sides. Okay, so let's call this point E, F, G, H, then I, J, K, L. Okay, first question is easy, right? Because we have EF is 2, EF equals GH equals IJ equals KL, which is 2, and the rest of the length, FG is 6, this side is 6, this side is 6, and this side is 6. Therefore, the perimeter is easy to find. So it's just 4 times of 2 plus 6, right? Which gives us 32. That completes the first question. For question B, find the area of the octagon. So we could break it to some trapezoid and a rectangle, right? For example, we could connect E and H and LI, and that'll break it into 2 trapezoid and Y one rectangle. So first of all, we could draw EH and LI. And again, that divides the octagon into two trapezoid and a rectangle. So we could let the foot of perpendiculars from F and G to EH be P and Q, because usually we need the altitude to find the area of the trapezoid. So FP and GQ can divide the trapezoid EFGH into two 45, 45, 90 triangles here and here, right? These two little triangles here, both of them are 45, 45, 90 triangles. And a rectangle FPQG, right? Thus we have FP equals EF over square root 2, and we know EF is 2 over square root 2. That gives us square root 2. Oh, sorry, that should be 1 square root 2, right? And then the area of EFGH. Can be divided into three parts. That's the area of triangle EFP plus the area of rectangle FPQG plus the area of the triangle GHQ, right? And we now know how to calculate each of them. That's just 1/2 of square root 2 squared plus 6 times square root 2 plus another 1/2 of square root 2 squared, and eventually that area is 2 plus 6 square root 2, right? And due to symmetry, we have the area of LIJK also equals the area of EFGH, which is also 2 plus 6 square root 2, right? And then we have the area of the rectangle in the middle, which is EHIL. And that can be calculated by using HI times length of EP plus PQ plus QH, right? And that's 6 times 6 plus 2 square root 2, and that gives us 36 plus 12 square root 2, right? Therefore, we know the area of the whole octagon EFGHIJKL is the sum of the three regions, which is EFGH plus HILE plus area of IJKL. And eventually that gives us 40 plus 24 square root 2, right? Okay, any questions? Okay, then let's have a look at the next one. Question C. Find the length of EI. Okay, we know HIL is a rectangle with side length 6 and 6 plus 2 square root 2, right? Therefore, we know the diagonal EI equals square root of squared 2 side lengths, which is 6 squared plus 6 plus 2 squared 2 squared, right? And that's 2 square root of 20 plus 6 square root 2 after simplification. Okay, have a look at the whole solution here. Let me know if you have any questions. Alright, question 18. The total number of degrees in the sum of the interior angles of two regular polygons is 1980. Sum of the numbers of diagonals in two polygons is 34. What is the positive difference between the numbers of sides of two polygons? Okay, so here we have some unknown quantities. We don't know the number of sides of the two polygons, so we could just let the number of the sides of the polygons to be x or y or a and b. So for example, we could write like this, like the number of sides of the two polygons be a and b respectively. Then, according to the given information, we have the following relationship. We have 180 times a minus 2 plus 180 times b minus 2. That's sum of the interior angles of the first and second polygons. And we know that equals 1980, right? So simplify that equation, gives us a plus b equals 15, right? Okay, what else we haven't used yet? We haven't used the second information here. We are also given a times a minus 3 over 2 plus b times b minus 3 over 2 equals 34, right? So simplify this equation will give us a squared plus b squared minus 3 a plus b equals 68. Okay, so basically you have two unknown quantities a and b and also two equations, which basically mean we could solve a and b, right? Okay, note that from the second equation we could know that a squared plus b squared equals 68 plus 3a plus b, and a plus b equals 15, so 60 plus 3 times a plus b, that equals 113, right? And then therefore we know 2ab equals a plus b squared minus a squared plus b squared equals 225 minus 113, and that gives us 112. So it's basically algebraic problem. And we also know that a minus b squared can be calculated by using a squared plus b squared minus 2ab, right? And we know a squared plus b squared is 113 and ab equals 112. 2ab is 112. So that equals 1, right? Okay, so we know the positive difference between a and b must be 1. Okay, have a look at the question here. Any questions, just let me know, okay? All right, then let's have a look at the next one. Question 19. Okay, in a patio, a pattern is determined by a regular hexagonal tiles, square tiles, and equilateral triangle. Triangular tiles, as shown in the diagram on the right. If the area of each hexagonal tile is 96 square inches, what is the number of square inches in the area of each square tile? And what is the area of the whole tile region shown? Okay, so we don't know the side length of the hexagon, right? So for example, we could let it be S to facilitate our discussion below. Let the side length of the hexagon be S. So we know the square and equilateral triangles each have set lengths as 2, right? So we know the area of each hexagon is 3s squared square root 3 over 2. We can calculate this easily if you know the side length of a hexagon, right? Therefore, the ratio of the area of a square to the area of a hexagon can be calculated as s squared over 3s squared square root 3 over 2, and this gives us 2 square root 3 over 9, right? And therefore we know the area of each square is 2 square root 3 over 9 times 96, which is 64 square root 3 over 3, right? Then as for the area of the whole figure, we note that the 6 equilateral triangles together equals area of the hexagon, right? Which means this area plus 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 this area equals the area in the middle here, right? And the 6 squares together have area of 6 times 64 square root 3 over 3, and that is 128 square root 3, right? Therefore, the area of the whole region just equals twice of the hex in the middle plus the 6 squares. And that gives us 192 plus 128 square root 3, right? You get it? All right, if no questions, let's have a look at the last one. Question number 20. Okay, first of all, let's draw a diagram to illustrate the situation here. We have a regular hexagon again, A, B, C, D, E, F. And we have some midpoints of each side, so let's call this point G, H, I, J, K, and L respectively. And we need to connect these points to form a smaller new hexagon. And we need to find the fraction of the area ABCDF to the smaller hexagon inside. Okay, so from the previous question, we know that we can easily find the ratio between triangle ABC. If you connect A and C, it's easier to find the ratio of the area of ABC to area ABCDEF, right? Can you recall that? And we know that area is 1/6, right? Well, if you don't know that, try to figure it out by yourself after this class, right? Because you could let one side length be S, and we could express both of the two areas in terms of S. Then you could find the ratio between triangle ABC and the whole area ABCDEF, right? The result is 1/6. And next we know that triangle ABC must be similar to triangle GBH, right? We also know the ratio is 2:1, right? Because G and H are the midpoints of A, B, and BC. Therefore, we know the area between GBH and area of ABC must be 1/4, right? Therefore, we know the area of GBH over the area of ABCDEF must be 1/24, right? And similarly, each of the 6 small triangles outside the regular hexagon the hexagon inside GHI JKL has area 1/24, right? That of the area of ABCDEFI. And therefore we know the answer is the desired ratio is 1 minus 6 times 1/24, which is 3/4, right? Okay, again, have a look at the solution here. Let me know if you have any questions, okay? All right, so that's all the questions we have went over so far, and the homework is to correct any questions you haven't done correctly before, okay? And next time we're going to have a look at the next topic. All right, so let's call it off today, and I'll see you next time. Bye.
Thank you. Bye.